All right, then, to wrap up Chapter 21, we get to cover the coolest stuff of all, biochemistry that has to do with you and me. So, diving right in, and now for something completely different. It actually isn't all that different, it's just a lot bigger. So, back in the day, when you were brand new OChem students, Cardi threw this table at you in Chapter 1. This is a table of the naturally occurring amino acids. So, just for review, this is an amino acid. Here's the amine, here's the acid. These amino acids have invariably this structure, where there is, on a 2-carbon chain, a carboxylic acid on carbon 1, and an amino group on carbon 2, and then a side chain. So the table shows you all the different side chains. If there are no side chains, if R is an H, then we're talking about glycine. But everything else, every other amino acid, has an interesting diversity of side chains, and that really changes up the properties of the biological materials that are made up from these amino acids. So, what do they look like? Well, if you think about it, an amino acid can react with another amino acid, and another amino acid, and so on and so forth, to make a polyamide. After all, amine plus carboxylic acid gives you an amide. And those polyamides are peptides, proteins, and enzymes. They're basically a lot of what makes us up, makes us tick. Here is an example of an enzyme, and I'm going to show you, this is the cartoon that most biochemists use to illustrate what this molecule looks like, but we don't like cartoons. We like atoms and bonds. So here's the cartoon again, but this is what it really looks like. This big old blob, and to make it a little bit easier to see, we'll show it in, it's kind of like line structure. So what you can see here, if we zoom in a little bit more, is that this thing is made up of a whole bunch of different amides, as you can see right here, and there's a very definite three-dimensional shape to it, and on occasion what we'll see as we zoom out, there's a place where something will fit in just right, being attracted by hydrogen bonds or van der Waals attractions or whatever to cause a biochemical reaction to take place. So this is what a polyamide looks like. Alright, so it's really important stuff, needless to say. The rest of the chapter talks about structure and synthesis. So what makes the structure so important? Well, as we've already suggested, the linkage of amino acid to amino acid makes an amide linkage, of course, and that's called the peptide linkage when we're talking about amino acids. So, if you look right here, this is an amide, and this is an amide. So there's two distinct peptide linkages in this particular molecule. But wait, let's look at this in a little bit more detail. Let's also look at the amino acids. There's one amino acid. Here's another amino acid. And here's our third amino acid. So we've linked together 3 amino acids via 2 peptide bonds to make this polypeptide. This is actually a tripeptide. What's particularly important about the peptide linkage is that, as you know, we've got the potential for resonance delocalization through that amide bond. That gives this double bond character. So that means there's really not totally free rotation about that nitrogen-carbon bond. There's some rigidity, and that rigidity is important. It lends itself to the three-dimensional shape of polypeptides, and therefore enzymes, and therefore life as we know it, pretty much. So that is the story of polyamides, putting together amino acids to make peptides and enzymes. Lingo-wise, the polypeptide has to end at some point, and there will be a C-terminus end and an N-terminus, obviously named because of the carbon and the nitrogen. The good news is, as you know, amides are at the very bottom of the reactivity ladder. So the fact that we are full of polypeptides and enzymes, that's a really good thing, or else we'd be kind of hydrolyzed into a oozing mass of who knows what sitting on the floor. All right, moving right along. Here's a great example of nature's handiwork. This is microcin, and it supposedly has 43 amino acids in it. Can we find them? Well, yes, we can, because there's the first one. Okay, so notice that I am always clipping the amide linkage. That is how I can tell where my amino acids are. So right here is a glycine, and it looks like I've got a lot of glycines in this molecule because, let's do this, we'll change colors on you. That's glycine. So this would be a good exercise for you. Take a screenshot, see if you can actually find 43 amino acids in here. So this is a peptide, a polypeptide that obviously has antimicrobial activity. All right, so the way these things are put together through the peptide linkage, and the side chains have everything to do with their physical properties, and the peptide linkage lends some rigidity to the shape. Bottom line is, especially if you take biochemistry, you'll learn this in droves. Bottom line is this primary structure of what amino acid is linked to what sets up the secondary and tertiary and quaternary structure. In other words, the whole darn shape of this really massive molecule. And that determines its properties in terms of what it's going to do in your body. So knowing the sequencing, aka the primary structure, is very important. And that's not trivial. The Edman degradation is a very clever way, tedious but clever, to determine what amino acid is hooked to what in a particular polypeptide. So here's a cartoon that shows this. The key reagent is this thiocyanate. Anytime you see a carbon that is connected via double bond to two electronegative elements, man, that is absolutely screaming electrophile. Just think CO2. Fantastic electrophile. So I've got a great electrophile, and I have a nice amine nucleophile, and so it attacks to give me ultimately this. So what we're seeing is a reaction here, picks up a proton to give me this intermediate. All right, this gray thing symbolizes the rest of the peptide. All right, so what? I've made this reaction. It's an easy reaction to do. What happens next is that this nitrogen makes this sulfur really nucleophilic, and so it can intramolecularly attack the amide carbonyl, and that ultimately cleaves right there, cleaves off what was my original amino acid. Okay, so remember, looking at the peptide linkage right there, the amide bond, the stuff that's in the orange circle is amino acid number 1, the amino acid on the N-terminus end of my peptide. Alright, so I've clipped off my amino acid. It's masked right here as this bit in blue. So what? Well, treatment of that intermediate product with HCl ring opens that thing, and ultimately it closes up in a, recyclizes in a different fashion to give a pretty stable, it's called a thiourea. So this thing in red is stable enough that they can analyze and compare it to other already made versions of the same. And so what you can see is I have identified my amino acid. This one is alanine because it has the methyl side chain. Well, once you've done that, you can then go through the whole sequence again and clip off the next amino acid and so on and so forth. So basically there's a big old library of these pieces that once they're made you can just simply say, yep, made that one. That was alanine. Alright, so that's how we can figure out what my protein, peptide, whatever it is, was made up of, how the amino acids got stitched together. But how can we stitch them together? Let's say I want to make a non-natural amino acid. Well, we have figured that out too, but it's not trivial either. So let's say I want to start putting together two amino acids like phenylalanine and cysteine. Well, easy peasy, right? I mean, all I have to do is, here's my nucleophile. I know I have to activate this. Don't worry about that, but no problem. Well, there's lots of problems. First of all, as we know, we have to activate the carboxylic acid. We're not going to use thionyl chloride anymore. We need something that's going to be milder and more effective, and that's called dicyclohexyl carbodiamide, aka DCC. And DCC, all of these reactions are reactions that are very similar to what we've seen in the last few chapters. Obviously, I can assume under acidic conditions that I will get protonation on my nitrogen and I get this product. Alright, turns out this thing over here in the circle is really a great activating group. So now instead of an acid chloride, I have this phenylalanine with this DCC addend. And so I ought to be very easy to just go ahead and, come over here, up, down, out, and we shall see that that should give me what is called dicyclohexylurea. This part is the urea part. That's really stable. Ureas are very stable, so that's why this should work great. But you know what? Things are always easier on paper. It's not that simple, because in reality, you've got the phenylalanine and the cysteine, and who knows how many other amino acids. They're all in the beaker together, and so kind of like what we saw with the aldol reaction. You can get phenylalanine reacting with phenylalanine, you can get phenylalanine reacting at the N-terminus of cysteine, or you could have cysteine reacting with the N-terminus of phenylalanine, and basically the bottom line is, crap. What a pain. Let's just let Mother Nature do it. Well, Mother Nature is all hands down much better at this than we are. There's no question. But like I said, sometimes we want to make non-natural amino acids. So to do that, we deal with the N-terminus and the C-terminus, and that leads us to solid phase synthesis. I'm going to tell you that this is important and fascinating and interesting, but you need to be more in tune with the strategy and how this works than the nitty-gritty details. So here is an example of a solid phase synthesis that was just recently published, and basically what I want you to zoom in on is a few things. Like, for example, this little orange ball is a resin, okay, a piece of plastic. upon that piece of plastic is hooked, in this particular example, an amino acid. Again, it looks to me like alanine. And instead of our Bach or CBZ groups that Cardy talks about, they're using something called FMOC, which apparently is the new and wonderful tag to put on these molecules. So I start with a piece of plastic that has an amino acid on it, and from that end I will build up my amino acid. So the next step, I add the same kind of protected amino acid. This one is apparently serine. So now you can see I put on my second amino acid. Now I'm going to add this special amino acid that's not natural. It's a really weird one that they made, and here it is. So this is solid phase peptide synthesis, and as you can see, step by step by step, you make a nice polypeptide. So, fascinating stuff. A lot of stuff in Chapter 21. Mechanism is all consistent. The learning objectives you should pay attention to are on page 1046. Biochemistry-wise, this part at the end, what do you need to know? Well, you should be able to predict what's going to happen if you throw phenylthioisocyanate in with your amino acid. So, more like a homework kind of thing, but you should go through the mechanism, make sure this makes sense. Be able similarly to write the mechanism and the products for any of the reactions in the Edmond degradation and this Merrifield synthesis. Just look at the reactions, make sure they make sense, and that you understand what's the nucleophile and what's the electrophile. It's really cool stuff. Okay, and then finally, just in general, be able to describe the big picture of how we can use solid phase synthesis to piece together a polypeptide of defined sequence. And that is it. No joke this time. You probably are relieved, and we will see you in class.